Hi, today I want to discuss about stereoisomerism in coordination number 4 tetrahedral complexes with monodentate ligand. We know that monodentate ligand meaning a pair of electron donor, one pair of electron donate to the metal ion. So now tetrahedral complexes in that stereoisomerism it shows one geometrical isomerism, second one optical isomerism. These two isomerism possible or not that we will discuss. So first I am taking one example, geometrical isomerism, that is cis and trans form. Cis meaning ligands are same side, trans mean opposite. Generally cis mean 90 degree, trans mean 180 degree. So I am taking one tetrahedral structure in that all bond angles are 109.28 degree. So taking two ligand AA, then changing their position. Otherwise we call exchange of any two bonds. Then if bond angle change meaning it gives a different structure. In case not change meaning this is a similar, that is called identical compared with the initial one. Therefore we can say these are same structure or identical. Identical means there is no change. So now I changed the position of A and bond angle is 109.28 degree. So there is no change. That's why first and second structure are identical. No change in the bond angle. When there is no change in the bond angle, that is called in tetrahedral complexes, geometrical isomerism not possible. Because we know that different structure means cis, first one means next one should be trans required. Therefore tetrahedral complex do not show geometrical isomerism. So second one I am taking the optical isomerism. For optical isomerism what is required? POS mean plane of symmetry and center of symmetry both should be absent required. Now I am taking one tetrahedral complex. Now I took the AA and another bond not mentioned in anyone you take that. Any two ligands are same in compulsory it contain plane of symmetry. Plane of symmetry denoted with the sigma. Plane of symmetry must be present if two ligands are same. Therefore, we have to check the next one center of symmetry present or not. Now I am taking the same structure with the same ligand. Then from metal to A distance is x, another is metal to A distance is x. Both are equal length. Two lengths are equal. When two lengths are equal, then we have to check that they are exactly opposite or not. But actually, tetrahedral structure up A and down that what do you call nearer to the observer A is not exactly opposite. Therefore, center of symmetry denoted with the Ci is absent. In tetrahedral complexes, center of symmetry is absent, and in tetrahedral complexes with the any two ligands are same in compulsory plane of symmetry must be present. Therefore, in tetrahedral complexes, any tetrahedral complexes with sigma and Ci both are present in optically inactive. Here given statement is a tetrahedral complex with all four ligands are different, then only a plane of symmetry absent. Anyway, whatever the ligands are present, center of symmetry 100% absent. Then we have to check which one plane of symmetry. If all are different, 100% plane of symmetry absent. Therefore, this is optically active. But keep in mind any two are same, optically inactive. Then now we have to check in the different molecular formula. One is complex geometrical isomerism and enantiomeric pair mean optical isomers and total number of isomers. Total number of isomers are calculated by sum of the geometrical isomerism and enantiomeric pair. Now I am taking the different formulas. Ma4 tetrahedral complexes. Geometrical isomer not at all possible because bond angles are not changed. Enantiomeric pair, here any two same, but here all four same, that's why 0. But one form is possible, that is one structure. Therefore, one isomer of the total. Then Ma3, at least two same required mean plane of symmetry, but here three same is there mean compulsory. Geometrical isomer not possible, plane of symmetry must be present. And sorry, in the geometrical isomer, bond angle not change. Enantiomeric mean all different required, but up to A2 appear mean that is compulsory. Optical isomerism not possible. Geometrical isomer bond angle not change. Only last one MABCD. In that geometrical isomer not possible. Optical isomer enantiomeric pair mean 2. Therefore total isomer 2 possible. That I am explaining with the example. MABCD, 4 different ligand ABCD. Now place the different position A, B, C, D different ligand at the different corners. Now we are checking the plane of symmetry present or not from the any side. I am taking one side here, any one side, all the side you have to check. Plane of symmetry sigma absent, cross mean absent, Ci absent, and therefore when these are absent mean its mirror image will be present. So its mirror image which is near to the mirror that appear first, that's why vertical as it is, therefore a position only, B will be first appear, and C, D are they appear behind that, that's why away. These two are called mirror image to each other but not superimposable, therefore these are called enantiomers. Each enantiomer is optically active. That's why I mentioned here each one is optically active. In case together 1:1 ratio racemic mixture, that mixture may be optically inactive, but separate they are optically active. Therefore, one is D form, another is L form. We cannot say compulsory first one D, next one is L. It may be first one L, second one D, but in general I represented. Next example, because in case you are not understand, actually I have to stop with the M, A, B, C, D only, but for other purpose, I explain here with the M, A to B, C. So here two ligands are same is there, therefore compulsory plane of symmetry present. Any two ligands same in plane of symmetry, sigma is present, therefore optically inactive. So I am not giving each one example, only with one sentence we have to understand. Any two ligands are same in 100% optically inactive. Geometrical isomer not at all possible because bond angle cannot be changed. This is a simplest explanation about the geometrical and optical isomer in tetrahedral complex with the monodentate ligand.